Okay, so good morning and welcome back. So it's time to tie together the things we prepared. And let me recall that we had the setting that we had a two-dimensional manifold which might have a boundary, might not have a boundary. For simplicity, I will go to the case where it is oriented, but in principle it could be even unoriented. And we had constructed a double. Now, there is the following principle, which goes in the physics literature under the name holomorphic factorization. And holomorphic factorization means that the correlator I want to find for the surface sigma should be an element in what the modular functor we are going to use assigns to sigma hat. So what is the modular functor? If you're familiar with the Reshetikhin-derived construction, take it. If you know Chern-Simons theory, then take Chern-Simons theory. This makes sense because this here is oriented in any case. This doesn't have boundaries. So this is really the easiest case of Chern-Simons theory, which assigns to a two-manifold a vector space. Now, how do we solve this problem? The first way I want to present today two different ways to solve this problem. And the first way is the following one. If we have not only a modular functor, but a fully fledged three-dimensional TFT, then this TFT will assign to any cobordism a linear map. Well, here I have a three-manifold, which is bounded by two manifolds. Now, I have problems drawing a three-manifold, so I'm drawing a two-manifold, and instead of a two-manifold, a one-manifold. And this will assign a map between the vector space TFT of sigma 1 to TFT C of sigma 2. Well, what we are going to do is we will construct such a three-manifold which only knows about our original sigma. This will be a three-manifold sigma, M sigma, which is called the connecting manifold. And this connecting manifold will have the property that the boundary of the connecting manifold is equal to sigma hat. Well, now this here is just a cobordism from empty set to sigma hat. That's what I want to construct. I haven't constructed it yet. So the TFT will assign to this, to the empty set, it assigns the ground field. Here it assigns the vector space in which we want to find a vector, and this is a linear map. Well, obviously, if I'm applying this linear map to 1 in here, which is a distinguished element, I will get a vector in TFT of sigma hat, and this vector will be our correlator. Put differently, if you dislike this mathematical way of putting it, suppose the Chern-Simons path integral has defined for you by somebody, then we get a vector in the vector space associated to the boundary by performing the Chern-Simons path integral over the three-manifold with boundary. But this is in a mathematically rigorous setting, which has the advantage that in the end we can prove theorems. Yeah, so we don't have to appeal to heuristics at any point. Now, we have to find such a three-manifold. And this three-manifold, well, if I'm just saying it has a boundary sigma hat, well, that's not enough. I don't want to add any topology to M sigma as compared to the two-dimensional topology I have already in sigma. So how do I do this? Well, the construction goes as follows. Take sigma hat. Sigma, this is a two-manifold. I'm getting a three-manifold in a trivial way by crossing with the interval. For convenience, I take the interval from -1 to 1. Now, here we have an anticonformal involution or an orientation reversing involution. If I would just divide out sigma, I would be in trouble because the manifold wouldn't be orientable, and there's no way to use a TFT or a Chern-Simons path integral on the unorientable manifold. But let's do instead, here the involution which sends t to -t. This is also orientation reversing, so the total thing is orientation preserving. This manifold is what I'm going to call M sigma. Now, let's investigate this in an example, just to get a feeling what the geometry of this is. And let's do this in the simplest example you could imagine. Let's take sigma a disk. For the moment, I'm not drawing any field insertions. Let's just do the geometry. Now, the double of this is a sphere. So this is a disk. This is a sphere. Well, now, and the sphere comes, this is sigma hat, sorry. The sphere comes with this orientation reversing involution. If I cross it with an interval, you can imagine what happens. It's a sphere which is thickened. Okay, I can't draw a thickened sphere, but I can draw a section of a thickened sphere. So what I'm now going to draw is, I'm drawing this in this way, that this is the fiber t is equal to 0, and this is the interval, and you take this and you let it rotate, and that's the figure we have. Now we have to divide out the reflection at the equatorial plane. Okay, so what is the reflection at the equatorial plane? That's the equatorial plane, and for any point here, I have another point here. I have just to be careful what's happening at the equator. So if I'm looking for the geometry of M sigma, I can forget what's going on the southern hemisphere. So I have to be careful what's happening here, because for the involution, these are fixed points. But here you see, this is the point where t is equal to 1, this is equal to -1. So this point and this point are identified. The point here, 1/2, and this point are identified. So what's going to happen? The points are identified in this way. So after this identification, we end up with something which looks as follows. And here, this interval here, this becomes a small interval which I draw dotted and which connects it here to the outside. So what you see is, this is a bit distorted, but the outside here is a sphere. And in general, you can easily check from the definition that the boundary is sigma hat, because before taking the quotient, I had two boundaries isomorphic to sigma hat, which I'm identifying. Inside here, I have the fiber with t is equal to 0. And you see, if this is rotating, you get a disk. Okay, so we have a map sigma into M sigma, and this map is very good because originally in our three-manifold we had these intervals by construction because we were crossing. These intervals survive. So you see, if I'm contracting the three-manifold along these intervals, then I'm getting back to sigma. So put differently, this manifold is, sigma is a retract of M sigma, and this was what I promised, that I wouldn't like to add any new topology. So drawing this a bit differently, for the next thing we want to do is, so the manifold looks as follows. Inside I have a disk, so there is a disk lying in the equatorial plane. There are these small intervals which go to the equator on the outside. So there are these intervals which I'm drawing here now in red, yeah, so these will be intervals of this type, and there will be intervals here, like the blue ones. I used already blue, no new color, so they will look as follows. There are two mirror points, and there will be intervals of this type connecting the two mirror points. Okay, good. So what is now my task? Last time I finished by explaining to you what is the decoration of such a disk. So we've now to go to fields. We will decorate this three-manifold with Wilson lines and couplings of Wilson lines, and then we get a specific vector in this vector space associated to the double, and I claim that this is the correlator. If I claim that this is the correlator, I will have to prove something, namely, the thing I get is invariant under the mapping class group and it obeys factorization. But I have the tools to prove it because this is an absolutely rigorous framework. Yeah, so let's go here to a disk. And let's take here two insertions in the bulk, because this corresponds to what we have here. And let's assume we have one boundary field. Now, I told you last time that I have to decorate the each two cell by a Frobenius algebra. So I have here a Frobenius algebra A assigned to it, and I will decorate the boundary here, which is oriented. I will decorate the boundary here by a module, while here it is a right module over A. Somehow I have to feed in the information what the chiral labels for the bulk fields are, because remember that the bulk fields come from combining left and right movers. So I have two chiral labels, and obviously you might be tempted to put I here and J here, but this looks a bit inconsistent, because how should an Wilson line labeled by I change into a Wilson line labeled by J? So I have to feed in the algebra, and the way I'm doing this is that I will take this surface here and triangulate it. And actually, I will take the dual of a triangulation. So what is the triangulation? Well, I will build up the surface from triangles, and the dual will be, I take here, where I have two cells, I take a zero cell, and where I take here the Poincaré dual. Yeah, so this will be the dual of a triangulation. Obviously, this continues. Now, I take this dual of a triangulation, I'm labeling these lines in the dual of a triangulation by the Frobenius algebra. Now, if I'm orienting this, and I have two ingoing and one outgoing vertex, I have the product of the Frobenius algebra, which I can put here. If I have one ingoing and two outgoing, then please remember that the Frobenius algebra had a coproduct. Yeah, so I'm taking the coproduct. So if I have enough data to label some triangulation by our Frobenius algebra inside this three-manifold. So this is labeled, there's somehow some triangulation. It can be more general than a triangulation, but never mind. Okay, first point. There's a beautiful fact of combinatorial geometry. If you have two triangulations, you can go from one triangulation to another one by a sequence of moves. These are so-called Pachner moves. And these Pachner moves, they boil down to two things. And let me discuss the most important partner move. Well, I can change a triangulation locally just by replacing this configuration by this configuration and not doing anything else. If I'm doing now my dual triangulation, I have to take my Frobenius algebra, which was in green. Let's take green. Yeah. So I have to put dots here. I have to put here products. And here I have to do the same thing. And then the pattern labeled by with the Frobenius algebra will change in this way. Now let's look at this a bit. Look, here, if I'm moving this a bit up, this will be for the Frobenius algebra. If this is ingoing, this is outgoing, which I can arrange, ingoing, outgoing, this goes in this way, yeah, suppose this. And this here will be, if this is ingoing, upgoing here, this will be this one. Now, these two things are equal, as we've seen yesterday, because this is expressing that acting first and then doing the coproduct is the same as doing the coproduct and acting. And the coproduct was a morphism of bimodules. So the wonderful fact is that this combinatorics of triangulation exactly plays with the algebra of relations for a Frobenius algebra. That's what we are using. So we are triangulating this, and it doesn't matter how we are triangulating it. The only point is we are triangulating it, really. It has to be fine enough. So then I have to tell you boundary condition. Well, a boundary condition was a right A module, but now I have a pretty easy time. If there is at a right A module an A line arriving, this is A, this is M, I have a very natural morphism here from M to M, because this is a module. And a module comes with a morphism from M tensor M to A, so I know exactly what kind of coupling of Wilson lines I should put there. I'm putting them, and now the last point to be analyzed is what's going on here at the bulk fields, where potentially I and J can be different. So there will be a line which is hitting this line. And at this line I have to specify a coupling. Let's see what this gives. Let's specify this coupling, and this goes as follows. Well, look, here I have an incoming I line, I have an incoming J line inside this plane. This is inside the horizontal equatorial plane. I have an A line coming in, an A line coming out. So this is how locally a bulk field looks like, and this is an algebra. Okay, so I have to be careful. When I'm just working here where nothing happens, then partner move versus Frobenius is doing the job that nothing depends on my choices. But here, at the field insertions, the same has to hold. So I have to be sure that if I'm connecting a line from the triangulation here or here, this gives the same result. And similarly from here and here. So you see, connecting here means that since this is coming from below, that I have to use an overbraiding here. Since this is coming from above, I have to use the other braiding here. This explains why I was writing down such a strange type of morphism for this here yesterday, which was this hom I plus A minus J A, and these were bimodule morphisms. Okay, now at this point you can go on. I should discuss what's going to happen if I have a defect line, and if I have different algebras on both sides, I will put bimodules, then I can put field insertions on defect lines and all this. Yeah, But let's look at this situation. What I'm getting by this prescription is a vector. It is a vector in the vector space in which I want to find a vector because this is a correlator. Okay, good. Now, a consistent system of correlators has to be invariant under the mapping class group and obey factorization. Being invariant under the mapping class group is very easy to see now, because if I'm applying the mapping class group, this pattern of the triangulation will change. On the other hand, by this interplay between Pachner and Frobenius, we know that if I change the triangulation, I still have the same value. And essentially, that's the reason why this vector here is invariant under the mapping class group. Proving factorization, on the other hand, is a nightmare because you have to take the gluing of two manifolds to transport it into the setting of three manifolds and do the appropriate transformations. This has been done, this works out, there is a proof, but I'm not going to show it to you. It's in this series of papers for good reasons in the last paper. Yeah? So here we have a construction of correlators which I would call a holomorphic construction. And actually, to give you a feeling, so what did we achieve at this moment? Well, we established a consistent set of correlators. Yeah? So this is a proof that in one class of quantum field theories, a consistent class of correlators can be found. So this is an existence proof, if you wish, for this class of quantum field theories. The remarks I would like to make now are the following. You can use this also to compute things. So for example, if you want to describe boundary conditions, then people were very much interested in one-point functions on the disk. Yeah? So this was called, the one-point function on the disk was called boundary states. And if you know the boundary state that describes a D-brane, you can read of all kinds of things, like, for example, the corresponding Ramond-Ramond charges. So it contains a lot of information. Yeah. Now let's go to the simplest case where our Frobenius algebra is just a monoidal unit. It's a decent Frobenius algebra. Now, well, what should we do? We have now to fatten this, put it into a sphere. Yeah, this is again the same picture. And then you see that the corresponding thing is I was drawing the bulk fields. I was drawing them in blue. So let's draw this in blue. This will be here. You have it only for I and I dual. And you have here a boundary condition. And it's an old result of Cardis from the 80s that the boundary conditions are, in this case, well, they are A modules in C, but what are modules over the monoidal unit? That they are in bijection to objects. Well, so what you have here at the boundary condition is another object M, and then the coefficients which contain this interesting information on boundary conditions, well, they were computed by saying, let's take the multiple to this state here, which is a two-point block on the sphere. Well, this two-point block on the sphere is the thing which people called back then Ishibashi state, and now you want to compute this multiple. How do you compute this? Well, this is reasonably easy. You take, if you have a full ball and you have another full ball, you can glue them together to get S3. So I'm gluing this, and I glue this with a full ball which goes, which is also I. So I'm getting here I have here my factor, which will depend on M and I, and here I get something which looks as follows. I have here, this will be an expensive talk for the Institute. And here I have M, and here I have I and M, and this is the Hopf-link. The invariant of the Hopf-link turns out to be the matrix SIM, which implements the modular group of the torus. And this is a way to prove what the coefficients are up to some scalar factor. They are just S matrix elements. From this you can do all kind of things. You can extract boundary entropies, you can extract Ramond-Ramond charges. So the information you are extracting is definitely worth something, but we are not computing the correlation functions as functions. So, yeah, this is something that was understood 20 years ago. There's no skein theory for the moment, so I should come to the title of the lecture series. Yeah? The problem here is twofold. The problem here is twofold. Using 3D geometry by just analyzing when you can define a 3D TFT forces C to be semi-simple. So we want to go beyond semi-simplicity. There's no reason why the category C, which we extracted from the representations of the vertex algebra, should be semi-simple. This is one thing, and the other thing is this is simply very complicated, and it's nice to have something simpler. So before doing this, let me just mention one development which was 10 years after this construction was discovered. Here you have a triangulation, and this triangulation is a bit invented. Yeah? So in the meantime, people realized that it is very interesting to consider surface defects in three-dimensional topological field series. So what you can do alternatively is you can put on this disk a surface defect. Now, if you put a surface defect, then these surface defects, which would be simply filling the disk, have the property that you can punch in a hole essentially for free. Essentially for free means there is a scalar factor, and the scalar factor depends on the boundary condition I'm choosing. So I'm just giving you the rough picture. Now, if I'm punching in many holes, you see that what's left is a triangulation or a generalization of a triangulation by ribbons. That's a way to understand why this triangulation by ribbons is really something natural. And now, once we are at this point, well, we want to have something simpler. And the thing I want to have something simpler is based on the following observation. Well, here we are working with the Reshetikhin-derived construction for the modular tensor category, and we apply it to sigma hat. Let's assume for the moment that sigma doesn't have a boundary, and probably I will stay with this for this lecture. Now, then sigma hat is sigma disjoint union sigma with opposite orientation. This here is a tensor product. The whole construction was compatible with tensor products, so I can write this as Reshetikhin-derived of C tensor Reshetikhin-derived of sigma and of sigma bar. The sigma bar here can be exchanged by taking here instead the reversed braiding. And we had a tensor product of categories. So this is Reshetikhin to arrive for C box times C ref on sigma. And now C had a non-degenerate braiding. And this non-degenerate braiding means that this category is actually something simpler. It is a Drinfeld center. So this here, in the end, is Reshetikhin to arrive of the Drinfeld center of sigma. It has been conjectured in the 90s and proven about 7-8 years ago that this here is the same as a state sum construction or a string net construction applied to sigma. So the idea is now that we can use a state sum construction to realize the TFT and then find the correlator there, and the state sum construction, or rather the string net construction, can be phrased in purely two-dimensional terms. So what is my next goal? I'm going to explain to you a nice construction of this vector space. Okay, are there questions up to this point? What are these Frobenius algebras concretely? Okay, good. So the point is, if I have an algebra is a module over itself. So, and this module describes a boundary condition. Now, if I'm looking at the boundary fields for this boundary condition, they will be exactly described by the Frobenius algebra. And since you're asking the question, I'm changing the order of my lecture. I will explain something, and then I come back to your question, and you are going to tell me whether I answered your question. Yeah. So so I want to explain that this Frobenius algebra has an interpretation as the algebra of boundary fields for a specific boundary condition. Yeah. So let me describe. Let me explain how to deal with the field content. So this needs a couple of notions which we need anyhow, and this goes as follows. So I try to explain to you that if I'm interested in boundary fields, I have a degeneracy space, I have a chiral label, I have a right module, and I have another right module, and these are module homomorphisms, and that describes boundary fields which change a boundary condition M to M prime and which have a chiral label I. And you see the fact that I take module homomorphisms is quite important, because from this side A lines labeled by the Frobenius algebra have to be attached, and it shouldn't matter whether I'm attaching here or here, but this is exactly the condition that I have A module homomorphisms. So if I'm now taking this here and I take the sum over it, I have all boundary fields. And it's a sum over simple objects. Now, well, let's take this, and this is what I will call BMM prime. This is an object in C, and I will transform the object. Well, I will transform the object by doing something which is for some people in the audience where I know that they have been exposed to more. this sum really is secretly a coend. So I can rewrite this as here, well, I have I acting on M tensor I. Now, such a coend, such a Hom, this can be rewritten. And I need an important notion, namely, there is the notion of an inner Hom. What is an inner Hom? Well, I can write this vector space where I is acting on M, which M prime. I can write this as a Hom space in C, I to some object in C. And that's called the inner Hom. And the inner Hom exists here. This is something you have to show. And by the way, everybody who has worked in some supersetting has worked with inner Homs. Let me explain this briefly. Yeah. So if you have supervector spaces, the morphisms of supervector spaces are degree-preserving maps. But obviously, you want to work at a given moment with matrices which have bosonic entries and fermionic entries, and they have a place in the theory as well. These are not morphisms in the category, but these are supervector spaces themselves. And they are exactly inner Homs in this category of supervector spaces. And they are defined by this, well, technically speaking, a junction. So I can rewrite this just to show you a bit of categorical, not magic, but standard techniques as the inner Hom from M to M prime. Maybe I should use the same capital or small m's in a consistent way, tensor I. Well, there is a single most useful lemma of category theory, which is the Yoneda lemma. The Yoneda lemma appears in many disguises. Here, one way to use the Yoneda lemma is to simply say that this is the inner Hom. Okay? So our boundary fields become something very simple. And the inner Hom, despite this bar, it behaves as it should. So there are compositions of inner Homs. In particular, the inner ends are algebras because endomorphisms are algebras naturally. Yeah? So what you see is that in a natural way, BAA is an algebra, and if you compute what it is, well, I'm just feeding in A, so it must be expressible in terms of A. It is A itself. So now you see that something important comes up here. You might have chosen a different Frobenius algebra than I, because there are various boundary conditions. Yeah, this has a natural algebraic setting. All these algebras we get are Morita equivalent. Yeah, so there's a natural Morita theory hidden in here, and which will also be used. So, did I answer your question what the A is?
I asked you later, I think. I shouldn't take your time now. I asked you in the break maybe.
Okay. But you shouldn't be afraid of asking. I mean, good. So now the bulk fields, they seem to be much more complicated. And it took us actually a long time to find a concise formula for the bulk fields as well. And I want to write it because it's this is a formula which is now 2 years old, and it's definitely one of the results I like a lot. So if I want to see what the bulk fields are, so the bulk algebra can be obtained from these inner Homs. These inner Homs are algebras, but which M should I take? Well, I should take all of them and integrate. And integrating means to take a coend. Well, if you know what a coend is, you know what an end is. Because, and you can ask me, why do I take an end, a coend, and not an end? And the answer is that here in this situation, end and coend coincide. So let me write this rather as M in A mod. And you can show that because the Hom and the co-Hom and the end and the co-end coincide, you can show that the bulk algebra is Frobenius algebra. So this is important because we want to have boundary and bulk algebras to be Frobenius algebras, because the Frobenius algebra has a co-product but also a co-unit, and the co-unit is non-degenerate, and that encodes non-degenerate two-point correlators on the sphere or on the disk, which is something very important in field theory. So this is constructed. Actually, this is an object in C, but for some reasons which are beyond these lectures, this object comes with a natural half-braiding, so can be considered as an object in the Trinfeld center. And this is an object which we call internal natural. This is a kind of an internal center, yeah? Because if you want to describe the center of an algebra, you can describe it in categorical terms in a similar formula. So all this is very natural, and unfortunately, if you want to know the details, you have to take a bit more of category theory. Yeah? So we have these field objects. We have here boundary fields. We have bulk fields. We could also write down defect fields. That's equally natural. And now I want to have a different realization of a modular functor. And what I want to do is I want to do this functor, which in a sense doubles things. So I want to do a state sum construction. Okay, so let's do something simple and direct. Well, what is the thing we want to do? We have a category where you should imagine representations of a vertex algebra. What was the essential structure I tried to extract from a vertex algebra? Technically speaking, I wanted to convince you that this is a pivotal, and for the experts even a spherical tensor category. Informally speaking, this means it's a category which has cyclically invariant tensors. So remember that we showed that if I have an invariant tensor and I put this up and I do this 3 times, then I'm back. Yeah. So by identifying all these, I'm thinking about such a cyclically invariant tensor in this way, that it is a coupling of x1, tensor x2, tensor x3, x4, x5 into 1, and it only the cyclic order matters. Of course, we have a bit more, and I will explain in informal terms what we have a bit more. And for example, we have a way that if 2 such tensors are linked by a line, and if I'm choosing vectors alpha and beta here, that I can contract the line and I know what kind of product of alpha and beta to take here. Yeah, this is a variant of a graphical calculus. If you want to know what it is, well, you decide to write this in more decent terms, to decide that this here is ingoing, one is outgoing, there is some alpha here, this goes into beta, there is something ingoing, and two things are going out, and you know how to compose morphisms in a category. So now we do something which has been invented by solid-state physicists when they wanted to describe topological phases of matter. Well, take sigma. Sigma is for the moment oriented, and let's go to the case where we do not have a boundary. I want to construct a vector space for this. So what do? Sigma looks like this, and I take a vector space which is very big. It is the vector space that is freely generated by all C-labeled graphs on sigma. What is a C-labeled graph? Well, I take these cyclic coupons. I take any number of coupons. This here would be already a C-labeled graph. Then it could be a more complete graph. I should say they are all finite graphs, but there are very, very many of them. And I should say I'm not taking graphs up to homotopy, I'm really taking all graphs. So this vector space is huge. It's not countably dimensional, right? And the idea is I don't want to impose anything by hand. Now, what are the elements of this vector space? These are linear combinations of graphs. Now, I have to impose some relation to take a quotient. What is this relation? Suppose I'm choosing some disk. Now, this graphical calculus here, if you develop it fully, it will lead you to the following thing. Well, this is a disk. Here I have such a graph. It will be maybe very complicated. It's a finite graph. But by contracting the edges, the vertices, and in doubt, there is a second move, which allows you also to fuse two parallel edges. Well, you can always evaluate this to a graph which has a single vertex, and then it needs 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 here. And of course, the labels are the same. Okay, so this is part of a graphical calculus which you can write down for any pivotal category. Pivotal just here implies that the canvas on which I'm drawing is only oriented, and that for the coupons a cyclic ordering is sufficient. Good. So we can evaluate this. Now, suppose I have a linear combination of graphs. They are all the same outside the disk. Then they are the same on the boundary of the disk. I evaluate them. I'm adding up the evaluations with the appropriate scalar coefficients, and suppose this is 0. Let's write this. So I have a linear combination of graphs. So this is lambda, gamma, and some graph gamma. This is a finite linear combination with never infinite things. And suppose that all gamma gamma restricted to the outside of a disk are equal, and that if I'm restricting them to the disk and evaluating them, this is what I want to denote by this, then they give all elements in the same Hom space, that this is 0, then I'm calling such a graph a null graph with respect to the disk D. Well, what you see is the graphical calculus is invariant under homotopies of the disk. So I already start to restore homotopies invariance, because it's at least invariant on homotopies of the disk. If you take a theorem from topology that any homotopy can be built from adding homotopies, building together homotopies localized on disks, you see that we have recovered some homotopy invariance. So homotopic graphs will give the same vectors. But we have divided out more, and we now take the vector space of all graphs and we divide out the null graphs, the vector space generated by the null graphs for all disks. Yeah? So the FC of sigma, and this gives, as it turns out, a finite dimensional vector space. So this is a finite dimensional vector space, and something I'm not able to show you is here that this is a vector space which is isomorphic to the vector space we had upstairs for the Reshetikhin-Toraev invariant, for the Toraev-Viro invariant. This is a vector space that's also isomorphic to the ground state space of a Kitaev model, if you have a Kitaev model. Now, what is the nice thing about this vector space? Two aspects. This vector space is generated by graphs or graphs modulo null graphs. So it comes with a geometric action of the mapping class group. Because the mapping class group are diffeomorphisms or homeomorphisms of surfaces. So if you apply a homeomorphism to a graph, you're getting another graph. And you take its class, and that's exactly the action on these on this so-called stringnet space. And what I want to say here is that this stringnet space is, well, it's a skein theoretic construction, right? It's constructed from skeins from graphs. So it has a geometric action of the mapping class group of sigma, and yeah, this is a first thing. And the second thing is we want to talk about specific elements in such spaces because these are correlators. But in a quotient, it is very easy to specify such an element because I'm drawing a graph and then I'm getting an element in this space. So what will be ultimately our idea? We are drawing graphs on a surface. This will give us elements in these vector spaces which we have seen describe the conformal blocks in which elements have to be specified to get correlators. So the whole business of describing the correlators will boil down to drawing graphs on a curve. And in a sense, that's the end of a long journey, and I have now to put a little bit of flesh on this construction. Yeah.
So, a quick question. C is graded, so the stringnet space happens to also be an algebra, because one can stack the stringnets on top of each other, so to say. Does this have any physical meaning?
This is an excellent question, and let me repeat it and expand it and then try to reply. So the first observation is the input for a derived zero construction is not a braided category, but it is just a category with a tensor product, a monoidal category. It yields the Trinfeld center, which is braided. So it seems that I have ignored the braiding in this construction. And the first answer here is yes, I ignored it, because if I want to describe the bulk fields, then due to the non-degeneracy of the braiding, due to this modularity, I'm working here with a category which has a trivial braiding. The fact that this is possible is, of course, highly surprising, and the price we pay is that this category doesn't have a direct interpretation in terms of vertex algebras. So this is a first remark, which is not really a reply to your question, because your question had a second part. You were remarking that if C is braided, then, let me phrase your statement in a different way. If C is not braided, then this is perfect for associating vector spaces to manifolds, and I was arguing this is what we want to do. If a category is braided, then the graphical calculus is naturally one dimension higher, because a braiding is naturally visualized in 3 dimensions. So there should be more structure, and your statement was that these vector spaces here come with more structure in this case. And quick answer, we are not using it. Honestly, I think there should be some meaning to it, because this structure is not there for nothing. And if you or anybody else has some idea about it, I would be very eager to discuss this. Yeah. So, Vincenta's question is a very good question, because it shows that secretly behind this story, I was doing a story which involves 2-dimensional CFT and 3-dimensional TFT. But behind the Reshetikhin derive 3-dimensional TFT, there's a 4-dimensional TFT. And the 4-dimensional TFT is something which we do not use in this picture, but which maybe can used for some good. And this 4-dimensional TFT, by the way, that's Schweigert TFT. Good. So I didn't answer your question, but it's a very good question. Okay, so now we have a new way to construct vector spaces for surfaces. This is not quite enough, because we have also to construct for 1 manifolds for a circle a category. And I will briefly explain how this goes, and then we have a short break. Is this okay? Yeah. So this is a very important construction that we will use to get a very handy description of the field content. So I want to associate a category to a circle, or any compact-oriented 1 manifold, but that's a disjoint union of circles. Now, I'm not sitting down and say, by hand, I'm assigning the Trinfeld center, which is the correct thing to do. What I'm going to do is, I take the circle geometrically, and what are the objects you could take? Well, you could take as objects finitely many points on it, labeled by objects xi in our category, which happen to be braided, but whose braiding we have forgotten. Now, If you look at these points, there should be some cyclic invariance of the circle. So somehow you would say x1, x2, and x2, x1, this should be the same. This looks like taking a center, but technically this is not useful. So what do? Instead, I take between two such circles, I'm defining what should be morphisms between a circle with, say, n1 points labeled by x1 to xn1 and n2 points. And what do? Well, I take string nets. So a morphism between this and this is represented by a string net. So this can be very complicated. Everywhere we have a point which needs to start. So this could be the string net, and I take string nets up to null graphs, of course. Yeah. So then you can convince yourself that if you compute the category, well, you only need 1 point up if you want to get a representative for any isomorphism class. And the graphs can be also contracted using the local graphical calculus. And you are ending up with graphs which you could draw in this way. Why do I draw them? Maybe some of you have seen the tube algebra of Vaughan-Jones. The tube algebra is exactly spanned by morphisms of this type. And it's known that representations of the tube algebra are the Trinfeld center. I'm cheating here, and I'm cheating in an important point. The Trinfeld center is not equal to this cylinder category, which I just constructed, but I have to complete it. And this is the last comment before the break. How do I complete such a category? Well, I'm simplifying by assuming that C is finitely semi-simple. In this case, you can complete such a category by doing a so-called idempotent completion. The problem of this category is that there are idempotents in string nets which have the property that they are idempotent, but they don't have an image. And there is a purely categorical nonsense to add such images. This is also called Karoubification. Karoubi is a person. And what we need to do is we need to take the Karoubification. Why is this important? Because the objects here in the Trinfeld center will be described alternatively by finitely many points on a circle plus an idempotent string net. Yeah, an idempotent string net. So this means a string net from here to itself, which has the property that if I do twice the cylinder, I put it together, I use the graphical calculus to simplify, I'm getting again a E. And we will be able to express the bulk fields in terms of such points and idempotents. Okay, so let's go back to bulk fields. And let's do something which is a bit more general, because we can have topological defect lines. And there can be fields sitting on such a defect line. A bulk field is just a specific example where I have the same Frobenius algebra here, and then there is a distinguished bimodule, which is A as a bimodule over itself. And for a bulk field, this wouldn't change. Now, obviously, you can ask the same question if you have here A and A twiddle, and we have here in B A twiddle bimodule. and here another a twiddle bimodule. Next thing you can do is you can say, okay, why are you considering this situation? Couldn't we consider the situation where there are more than two defect lines joining? Yeah? Well, why not? Yeah? So what we will have here is we will have a Frobenius algebra, a special symmetric Frobenius algebra in each of these patches. We will have bimodules here, and now I have to find for such a configuration a natural element in Z of C, yeah, because this is in our situation C box times C ref, so it will give rise to something that has left and right movers, but I will find it by using the cherubification of the cylinder category. And so how do I find here in this situation something in the cylinder category? Well, first of all, I replace this point by a little circle. Then on this circle, I have, in this case, 4 objects. Okay? So I have 4 objects. So taking the same picture as above, I take B1, 2, B2, 3, B3, 4, B4, 1, and I forget that they are bimodules. Yeah? The objects here are pairs consisting of such a set of fields and then an idempotent. So I have to find an idempotent for you. And the idempotent can be found very easily. Namely, let's take this circle we are interested in. Let's do a cylinder over the circle, and let's put straight lines for this object. So here, for example, I have B1, 2, B2, 3, and so on. This is an idempotent in the cylinder category, but it's the identity, so this is not interesting. Moreover, I've forgotten for the moment that these are bimodules. So, but here, remember that here, for example, I had a Frobenius algebra A1. How do I add, and here I had a Frobenius algebra A2 and so on. How do I add this? Well, this is a left module, so there is a unique coupling here which expresses the action of A2 on B2. There is all the right action. I do the same for the left action. Now I have 2 lines labeled by A2. And what I'm now doing is I'm joining them by using here the co-product of the Frobenius algebra, and here the 1. If you have worked with special symmetric Frobenius algebras, you will see that this is an idempotent. If not, then look at this situation. I have here these 2 lines, and between the 2 lines I have the co-product and here the unit. Now suppose I take twice this, which means I'm taking the cylinder, I'm building the cylinder again, which means that from the next cylinder there will be another such line. Let's check that this can be replaced by a single such fork. Well, why can this be replaced? Well, first observation, these are actions. And for actions, I can replace this by doing a multiplication. And similarly here. And then I get here this beautiful heart-shaped thing. And now you have to transform it. You can use the rules you have for a symmetric Frobenius algebra to transform it to something like this. This here is the 1, the unit, and here you have such a bubble. And for a special Frobenius algebra, any such bubble can be removed. So it is an idempotent. So what we are getting is for a type of defect fields, which we call here, this type of defect field is something we called multi-branched defect fields. We get, in a very natural way, objects in the Karubification and hence bulk objects. Okay? So, now I should tell you how to get, in the stringnet approach, the correlator. And I'm going to do 2 drawings, and the drawings are also in the lecture notes, so maybe I have to simplify them, and I'm adding a few words. So, actually the first thing is there are tricks to take into account boundary fields. And since there are some people who have been exposed to more of this theory, let me just say boundary fields are objects in C. If you have the Drinfeld center, you have a natural forgetful functor to C. The forgetful functor has a left adjoint and a right adjoint. The situation here is unimodular, so there is a unique functor in this direction. And we are describing the boundary fields by using this also as objects in Z of C. This is just to show, to give you a feeling that with a bit more theory, you can really do all correlators. So now, let's suppose that we have a surface with 3 insertions, and it could be a pair of pens, but let's assume it's a bit more complicated. And let's assume that there are defects. So here I have an insertion, say 1 insertion here, and this insertion has a defect line is starting here, and then I have another defect going from here. This is almost not visible, I'm afraid. Maybe there is also some defect line which just goes around here, and I have to choose decorations. So what I'm choosing here is, for anything that's in here, I choose a Frobenius algebra A1. For all the other 2 patches, I'm choosing Frobenius algebras, and so on. And now I want to get, so this is essentially the decoration of a worldsheet. Yeah? So this is, and worldsheet is for me, independently on string theory or whatever, it's the type of geometry I need to define CFT correlators. Yeah? Good. So now from this I get a stringnet as follows. I take the same geometry and now you see, in order to get my fields here, so here for example I have a disorder field where I have an ingoing and an outgoing defect line. Well, I need the projectors. Yeah? And I need to take care of these Frobenius algebras. So what I'm going to do is, inside, this is too sloppy, so this is my hole, this is my green line. I'm taking this 2 patch and I'm again triangulating it. I'm triangulating it by using some triangulation which labeled by A1 lines. And I'm doing some similar things, and it should be fine enough, and fine means that the value doesn't change if you are adding more triangulation lines. So, okay, so I'm doing this here with A2 lines and so on, and then automatically these projector lines exist because they are inside the surface. And this gives me a very complicated stringnet, but it gives me a stringnet, and as a stringnet, it is an element in this vector space which we identified with the vector space in which we were working previously, the vector space for the double. And what you can show is this is exactly the same vector. So what you do is you get a description of CFT correlators. You are writing down the decoration data that I described. You are replacing the two patches that are labeled by an algebra by a triangulation. You take one of these string nets, and that's the correlator. And this is a purely two-dimensional thing. I'm never drawing anything in 3 dimensions. So I'm avoiding the 3-dimensional world. If you have string net constructions that work in more general settings, and that's what people are about to develop, and there have been several papers on this recently on the web, you will be able to use these string net constructions to address more general classes of CFT correlators. So that's an important future potential for future developments. And then you get CFT correlators. And now it's surprisingly easy to prove invariance under the mapping class group. And it's again about triangulations, but these string nets have also factorization properties. Namely, if you have two string nets where at the boundary they have the same boundary value, you can sew them together and get a new string net. And these maps, which take the surface before sewing to the sewed surface and the corresponding map between the vector spaces, that's exactly the structure map of a coend, and that's a very neat formulation of factorization in which you can prove factorization of correlators. Good. So now comes the last part of this talk. The first thing is we can now compute a lot with correlators. And compute means also we can make structural comments. So one thing you can do now is you can study implementation of symmetries of a TFT in terms of defects. So let me explain this. And this is something which people are now playing in higher dimensions. This is what string theorists call these days the symmetry revolution. And in the context of CFT, two-dimensional CFT, these are 20-year-old theorems. Yeah, so how does it work? Suppose, for example, you have, you're studying a 4-point correlator. And let's do something on a sphere. Let's do something very simple. Let's study this in the Ising model. Ising model is something many of you have seen. So it is a category C which has 3 simple objects. And one of these simple objects has the property that if you tensor it with itself, it's isomorphic to the monoidal unit. Yeah? The Ising model has a symmetry. And the symmetry is spin up and spin down, exchange it. Yeah? So now what you can do is take a loop labeled by epsilon and insert a corresponding defect. Well, what you can prove in this context is that this changes the correlator up to a scalar factor, which is the dimension of epsilon, but the dimension of epsilon tensor epsilon is equal to 1, which means that the dimension of epsilon squared is equal to 1, and if the dimension is positive, which we want to assume now, I have to multiply by 1. Okay, so now what I can do is I can deform this defect. So after a deformation, this closed loop can look as follows. I've deformed it, so it is closed here and here. and the value didn't change because I just deformed the correlator. Now, let's see. I have here epsilon, and you see that here at this bottleneck, they have opposite orientation. In the fusion of epsilon and epsilon, I have just one, which means I can locally replace this. This is a skein relation, but the fact that they are equal, that's a theorem. So the correlator doesn't change if I'm replacing this locally, and you see I've here now changed the bulk field insertions by wrapping them with a codimension 1 defect. Of course, I can go on. I'm shifting this here until I have the same situation here. I'm doing the same game here. And in the end, I have this loop which has dimension 1 and which disappears. So what do I show? What did I show? If you are looking here at things which have an inverse with respect to the tensor product, you get symmetries of correlators. So these are very good symmetries in the sense that you also know what to do on a boundary condition, because you can fuse such a Wilson line to a boundary condition. So what you see is that categorical symmetries are invertible, and now here actually in the Ising model the relevant algebra is the monoidal unit, so A bimodules internal in C. That's a group. You can compute this group, and all this is old stuff. This was essentially, I don't know exactly when it was on the archive and published, but this dates back to 2004. This is work by Jörg Fröhlich, Jürgen Fuchs, Ingo Runkel, and myself. So categorical symmetries can be identified with invertible bimodules, and the fact that the correlators are equal is a theorem. Once you have symmetries, you are asking about dualities. The Ising model has a duality. It's an order-disorder duality, and disorder duality, if you think about the Ising model as the critical point, it comes from a high temperature, low temperature duality, from a Kramers-Vanier duality. So, can you recover such dualities at the critical point? Well, you can. Let's look at dualities. This here has a special property that if you take the fusion, then the fusion rules are of this form, and here you have only invertibles. Only invertible objects. Whenever you find in your A bimodules, a bimodule which decomposes into a direct sum of invertibles, you have a duality. Let me demonstrate this. It's roughly the same argument, plus one extra information which has to be proven, but which I'm not going to prove, but I'm referring you to the original papers. So, again, let's take the 4-point situation. I start by inserting such a loop. Well, in this case, the quantum dimension is square root of 2, so I can cancel this. Now I'm deforming, and then after deformation, I'm getting again in this situation. And now you see that we have here our psi and our psi. This is a self-dual field. So, and what happens is that here I cannot say anymore that this thing holds, but instead what's going to happen is that I have to encircle this, and it turns out that the condition on defects is such that there will be a line labeled by epsilon emanating here. So this is if I'm pulling it over, I'm getting here something which is not a bulk field anymore, but where you have a defect line starting. For people in statistical mechanics, these are perfectly reasonable things. These are disorder fields. Disorder fields are fields where defect lines start or stop. So if I'm doing this again, then it turns out that what you are getting is here a configuration where you are getting from the bulk fields are replaced by defect fields, and we are getting here something which contains defect lines, but we show our defect fields, or since it's only one defect starting, the terminology is disorder fields. So we get the equality of a correlator of bulk fields and a correlator of which involves disorder fields. So we get order-disorder duality. And this is a theorem, and it's even better than a theorem, because we have here an algebraic reason which generates such dualities for us. And this is another application of these results. So you see, you can really do field theory, and you see that it is quite natural to work with these defect fields, and these defect fields encode categorical symmetries. Okay, I'm coming to the last part of the talk, let's look, to start it, let's look at this picture here. I try to convince you that since this fuses only to the invisible defect, these two configurations are equal. So now, if you think about this, and one of our PhD students was thinking about this very carefully, he said, this is a severe puzzle. Because let's suppose I want to compute a CFT correlator on an annulus. Well, we can do this. Let's suppose that the annulus has such an invertible defect, and it actually has two of these invertible defects. And then this configuration is in no way you can distinguish it from this configuration. It's the same. Please tell me what is the mapping class group. And you will see the mapping class group here looks bigger, because you can turn the inner disk by 360 degrees or any multiple. It doesn't change the configuration. But if you do it here, it changes. So Yang was asking, so what is the mapping class group? How do you define it? Just defining it by saying it keeps the defects fixed, this is nonsense. This is not invariant. And this is the beginning of the last story I want to tell you. And this story gave a surprising insight, which I consider a physical insight. So here you see I have two of these worldsheets. Yeah? Here I did something by replacing patches that are labeled by triangulations. Now, actually, I was mentioning yesterday on purpose the word bicategory. And there is a very natural bicategory in the game. And this bicategory is the following bicategory. I call it FROB-C. It is a three-layered structure. It has as objects special symmetric Frobenius algebras. As one morphisms, it has bimodules. And as two morphisms in layer 3, it has morphisms of bimodules. Yeah, and this is a very nice category. And well, what you can check is this is not only a bicategory, it is a pivotal bicategory. So before we were using a graphical calculus where, well, essentially we use boxes and then there are objects, and here we have a morphism from U tensor V to X. Well, what we now do is we go beyond something which labels only one manifolds and coupons. We also label the two patches. So we get a skein calculus in which also two patches are colored. This makes sense. This has to be developed. Well, leave it to the experts to develop it. And check our paper. If you find mistakes, you're an expert. Yeah? Good. Now, if you have a local calculus, you can do a string net construction. By the same thing, you take all possible colorings of your surface with some graph on it, and you identify it if it agrees locally on a disk. So in this way, we get a new string net construction. So we have a string net construction based on the bicategory Frobenius of C, which assigns a vector space to a surface. And we have our old string net construction, which I was discussing earlier. So how are the two related? Yeah, so now here's another bicategory. It has just a single object. It has here objects of C, and it has morphisms of C. This is what's commonly called the delooping of C. Okay? Now, I take a Frobenius algebra, I simply send it to this object. No choice. I take a bimodule, I forget that it was a bimodule. I take a morphism of bimodules, I forget that it was a morphism of bimodules. So I'm getting a nice two-functor between them. And then it turns out, well, it is not a two-functor. You have to check all axioms of a bicategory. A monoidal bicategory is a huge package of things if you unpack it. And it turns out that it is something weaker. It is a so-called Frobenius monoidal functor. A Frobenius monoidal functor is a special case of what people ironically called a linear functor. Linear functors were introduced. It's not a functor between linear categories, it's a functor between linearly distributive categories, and they were introduced in logic, in a field which is called linear logic. And the whole word linear is a misnomer here. Yeah, so what such a functor is, it is weakly monoidal, it is weakly opmonoidal, and it has consistency conditions. And these consistency conditions, they transpire in such a way that there is a good relation between these two string net spaces, provided I'm compensating by this Frobenius triangulation. So now we go to the following picture. If you take a worldsheet like the one above, it gives almost by definition a vector in this vector space. Why? Because this vector space is written as a quotient of the vector space generated by such worldsheets modulo local relations. This vector, so here for any worldsheet S, I get an image in here. And it turns out that whenever two worldsheets here have the same image, they have the same correlator. So the correlators factor through this map. So if you think about the CFT as a way to determine a worldsheet geometry, the CFT will not be able to distinguish two worldsheets which determine the same class in this vector space. So something new is happening, and I think this is of interest for physics. We are constructing here a vector space purely from defect data. So what we do is we take topological defect data, we take local relations, and the correlators factor through this. So poetically, we decided to call this here a quantum worldsheet because this is the only aspect the CFT, the quantum field theory, sees from the classical geometry you have for the worldsheet. And then the correlators factor through the quantum worldsheet. They are indistinguishable. No way to distinguish them for the correlators. And now it turns out that these two worldsheets, they specify the same class in this vector space of quantum worldsheets. And now you are looking at the stabilizer of a vector here under the action of the mapping class group. And that's the correct definition of the mapping class group with defects. And this mapping class group, this object here, has a bigger stabilizer. So the correct mapping class group contains the Dehn twist. The correlators are invariant under it. And so this question about asking what is the mapping class group, which looked like a technical question, it led us to understand that correlators factor via a vector space that is defined in terms of defect data. Whenever the defect data, topological defect data, are locally the same, the correlators are the same. And this could be a principle of quantum field theory that's more stable beyond two-dimensional CFT. Of course, it's not easy to turn it into theorems. All this here is proven, yeah, so with a lot of technology that I was hiding, but I think still you can learn something more general. And maybe that's a good point to end the lecture.
Questions? So, if I understand correctly, like the upshot of all this is to define a CFT as such a system of consistent correlators.
Yes.
Like how much is known about the equivalence of such a definition to, or like the construction of such a set of consistent correlators from like more traditional physics data, like an action principle with like fields and an action of a conformal group.
Okay. Well, wherever you can compare, and one class where you can compare is for Wessumino-Witten models, so models which are defined on group manifolds. The things you can compute, like for example, coefficients of partition functions, OPE coefficients agree. Now, this is of course a necessary condition that the thing we are talking about makes sense, both on the action side and on the side of this construction. But actually, I think the parallels go a bit further. And maybe I'm briefly expanding on this, and I'm trying to spoil a bit Peter Bauknecht's lectures. I don't know what Peter is exactly going to do, but let's do this. So for example, if you want to, let's go to Wessumino-Witten models, because this is something you might have in mind, yeah? So A Wess-Zumino-Witten model is described in terms of a gerb on our group manifold. It could be other than a group manifold, but with a group manifold we can calculate, yeah? So this is a bundle gerb with connection. Now, a bundle gerb with connection is something, how to say this? Let me give you a rough picture. So Peter was talking about surjective submersions. If you talk about surjective submersions, what's going on is you can define multiple fiber products. That's something we have seen. At this point, Paolo was asking, is this a new definition of a manifold? And I would say, well, it is not, maybe not a new definition of a manifold, but what it is what you have here is a simplicial object in manifolds. And Lie groupoids are specific simplicial objects in manifolds. So we could think about this as an indication that we might better work with simplicial objects in manifolds. Yeah? So that's, now for a bundle gerb, what you have is, you don't have transition functions, you have line bundles of transitions, and you have a multiplication here. This is, yeah, and it obeys some associativity condition. Now, let's suppose you are interested in dealing with Wess-Zumino-Witten models not on oriented manifolds, but on unoriented manifolds. This is necessary for type 1 strings. Yeah, so, and it's a mathematically reasonable problem. What do you do in our approach, and what do you do with gerbs? Well, what you do is, in our approach, you need an identification of A and the opposed algebra. And this identification is not really an algebra morphism, but it's an algebra morphism. It's not really an involution, it's an algebra morphism, but it's an involution which, for technical reason, squares to the twist on the algebra. Now, you can start to implement the same idea for bundle gerbs. And you will have to write down a bundle gerb with an additional structure which identifies this involution and mu to the -1. This can be done. This gives a consistent notion, and it gives a notion of a bundle gerb which allows to define a surface holonomy on unoriented surfaces. So you see there's a structural similarity that we have algebras determine, at least for the topological terms of the action, yeah, so I'm focusing on them. And we have here algebras with involution. For boundaries, I was telling you that boundary conditions are objects in A mod. What happens if you want to describe boundaries, so a sigma model with boundaries in the, where you have a topological term described by a gerb? Well, what you need to do is you have to introduce the notion of a gerb module. A gerb module is something where you have now, for this multiplication, also an action, and typically this doesn't exist. It exists only on a submanifold, and the submanifold is the world volume of a D-brane. So you see that at those points where the sigma model is accessible by existing mathematical notions, structural similarities come up. I don't know why, I don't know how to exploit them up to a certain point, or beyond a certain point, but at least understanding here these topological terms in an action can be done in a picture that's surprisingly similar to what I showed you here. And there must be some deeper reason for this. But obviously we are not technically at the point that we could start a real comparison. But we took this as an indication, and we tried to simply push this parallel to the extent we could push it. Yeah? So maybe this shows that you can prove theorems here, but you can also learn something structural which should be of interest beyond this class of theories. Yeah?